Hello there, welcome to instalment 3 of what the critics are calling the third instalment of the amount of substance, i.e. the mole, past paper questions. Once again, these are taken from OCR, but plenty here for every specification. Moles are just moles. Here are the equations again. You know what I've said about Avogadro's number. Use the value given to you either on a data sheet or in the question. And there may be some slight variations in the particular letters which are used for each variable, but they're the versions that I will be using for this video and for all videos. Okay, so here's a question. It's a rate question with a moles bolt-on, and it's an exercise in basically keeping your nerve and making sure that you just get to what is relevant. So we just got an excerpt from this question that we're going to look at today in this particular video. So on the next slide, I've just abridged it. We've got a volume of oxygen measured over time at RTP, so that's going to give us an indication that we need to be aware of the molar gas volume. Oxygen is obviously a gas. We've got a concentration and a volume of hydrogen peroxide, H2O2, and the concentration, that's what square brackets mean in this context. The concentration of H2O2 is determined at each time. It's measured at different time intervals, and there's the plot. And as we can see, it's a standard rate time, it's a standard concentration time graph. The concentration of the reactants diminishes or it gets less as time proceeds. So what do we need to do? Determine the total volume of oxygen measured at room temperature and pressure that should be prepared to collect in this investigation. So how are we going to go about doing that? Well, the answer is moles and moles calculations, amount of substance. Let's take a look at what we have. We've got 25 centimeters cubed, which is a volume, and we've got 2.30 mole per decimeter cubed, which is a concentration. So we can work out the amount of hydrogen peroxide in moles. Number of moles of H2O2. We've also got a balanced equation, so we can get to the amount of oxygen using stoichiometry, using reacting amounts. It's a 2-to-1 reaction. And then from the amount of oxygen, we can work out the volume of oxygen, because we know that 1 mole of a gas occupies a very specific volume under conditions of room temperature and pressure. So number of moles of H2O2 is concentration times by volume. Because it's a 2-to-1 reaction, the amount in moles of oxygen is half the amount of H2O2. And because we're working in centimeters cubed, the volume of oxygen is going to be 24,000 multiplied by the amount in moles. Notice that I haven't used my calculator yet. That is showing you working out rather than just writing down different numbers or in process results. RTP, as I said before, that just tells us that 1 mole of a gas is going to occupy 24,000 centimeters cubed at that temperature and pressure. So now the numbers go in. Instead of times 10 to the minus 3, I've just simply divided by 1,000 there for that 25 centimeters cubed. That's going to convert it into decimeters cubed to be consistent with the units of concentration. And that gives me 0.0575 moles. It worked out exactly that, but if it was a couple more decimal places which were not zeros, I would include those in my in-process results. It's a 2-to-1 reaction. So therefore, if I divide that 0.0575 by 2, that gives me the answer of 0.02875, which is the amount of oxygen. And then to calculate the volume of O2, I simply multiply it by 24,000, gives me an answer of 690 centimeters cubed. What sort of apparatus would you use for that? A pretty big gas syringe, a 1 decimeter cubed gas syringe, or maybe even a 1 decimeter cubed measuring cylinder. If we're going to, so either we can collect the gas directly in a gas syringe, or we can do it by the volume of water which is displaced. So that would be the apparatus that would be appropriate to collect that volume of gas. Okay, thanks for watching. Any questions, welcome. Just send me an email or put something in the comments.